Hey, welcome back. So what we're going to be doing right now is starting in on some examples and then fine-tuning a couple of the thoughts about hypothesis testing in chapter 20, not 20, in chapter, what chapter are we in? 7. Different book, chapter 20, this book, chapter 7. Okay, so let's move forward a little bit, and we've got our example of the non-returning college students, those that could be finishing up if they simply were to complete their senior year. Now, frankly, that's sort of a waste of state resources. The state of North Carolina said they really want to have their students finish their senior year because so much money had been invested in their education because it's state supported. They want to sort of figure out why students don't return for their senior year. And so again, we've got a sample of students 42 who do not return for their senior year. And we've got a sample of students who do return, non-returning, and then the returning students. Null and alternative hypotheses. Well, again, the null hypothesis always must have an equality built into it, and the alternative hypothesis does not have an equality built into it. So my null hypothesis, H0, and again, my Apple Pencil is not working well, so that's with my fingertip. Okay, null hypothesis, HO colon, alternative hypothesis, HA, again with a colon. The null hypothesis is the logical opposite of the alternative, and the alternative is usually a natural question. Is there a difference? So mu for the non-returner students, mu n, is equal to mu for the returner students, mu r. Oh, no, alternative, not equal to. And for the null hypothesis, I'm going to have mu n equals mu r. Again, those are my two choices. My test statistic t is equal to y bar for the one group. And I'm going to go with always the larger sample mean first. Y bar for the returner students, r, minus y bar for the non-returning students, n, over then the standard error, which is SR squared over NR plus SN squared over NN. And that is, once I plug some numbers in, 3.22 minus 2.41 over then the root of, in this case, 0.93 squared, 0.93 squared over then 42. I'm sorry, 48, I apologize, 48, plus then 1.03 squared over then the 42. So at this point in time, I'm going to pause the recording so that way I can do this in my, my calculator, and I'm going to get right back to you. So you probably want to pause yourself and verify that you can get this number yourself. Pausing.
Yeah, 2 pounds.
So I got as my answer 3.89. So I'm going to write that down and hopefully go with a different color. 3.89 is my t value. And degrees of freedom, it's the larger of the two sample sizes. No, the smaller of the two sample sizes, -1. I'm going to go with 41 degrees of freedom. So I need to use the t-table with 41 degrees of freedom to get my answer. So maybe I've got the t-table lying around. Let me grab that, drag it over here, and we could utilize it to get our answer. So again, there's a little bit of clutter on the screen, but 41 degrees of freedom, it's going to be found in this row here. Okay, so the row entitled 40 degrees of freedom. And I'm looking for the number 3.89 somewhere in that row, 3.89. And I'm spotting, as we move to the left in this row entitled 0.40, as we move to the left, three point eight nine is to the left of you in that, 3.89. So my upper tail area is less than 0.0005. Yeah, literally from 3.89 and up, that upper tail area shaded in there is less than 0.0005. And the corresponding lower tail area from negative 3.89 and down is also less than 0.0005. My p-value is less than 0.001. 1 in 1 in 10, 1 in 100, 1 in 1,000, less than 1 in 1,000. Oh my, that's a mess. Okay, so let's sort of figure out with my p-value of less than 1 in 1,000. Okay, what would you conclude? My test statistic t is 3.89. My p-value is less than 1 in 1,000. That p-value allows us to say either the null hypothesis is true and we saw something so freakishly unlikely that it should never happen but for 1 in 1,000 such studies, or you can believe the alternative hypothesis. My p-value here is less than alpha 0.05. My conclusion is I'm going to believe the alternative hypothesis. I believe that the students who return and those that do not return have different means. Again, the mean of the returning and the mean of the non-returning students is different. So the population average is different. Okay, so the t-test and the confidence interval for the difference of two population means are actually related. They both are ways of comparing mu1 and mu2. And I'm going to say if the confidence interval, the list of plausible values for mu1 minus mu2, if 0 is inside that confidence interval, we cannot reject the null hypothesis of equality of the two population means. Mu1 minus mu2 might actually equal 0. Again, if the confidence interval for the difference includes 0, 0 as the difference of population means is not out of line. The two population means might be the same. However, if the confidence interval includes, it does not include 0, if the confidence interval does not include 0, then I have a reason to think, okay, that the two population means are, in fact, different. So I've got data here that I'm going to bring up, and let's see if I can grab the right data set. Let's maybe start with our ice cream data, if I can find that. Open file. Open. Which data set do I want to go with the ice cream? Ice cream. I begins ice cream. H-I-J-K-I. I'm not finding the ice cream in that data set folder. I have to find a different example. Shoot. Searching, different location. Okay, there we go. We've got the data on the ice creams. Again, the vanillas and the chocolates, two different categories of flavor. If I were to do my hypothesis test, it's going to be done with fit y by x. Again, virus, we don't do this in our class. We're not requiring you to use the software, but calories may depend on the flavor category. Do calories depend on the flavor category would be my hypothesis way of phrasing it. My confidence interval way of phrasing this is how do the calories depend on the flavor category? In either case, I click OK. And then after I've hit the OK button, I'm going to go ahead and just turn on that t-test procedure. We can see, among other things, like before, the confidence interval for vanilla calories minus chocolate calories is -19. I'm sorry, -37 to +19. 0 is inside that confidence interval. 0 being inside the confidence interval says we would not reject the null hypothesis of equality. Well, our p-value 0.5 says you don't reject the null hypothesis of equality. It's not below that 0.05 value. So let's try another example. And see if I can grab the right one. Not there, but in a different folder. You know what? I have stuff in so many windows open right now. It's very frustrating for me. But oh gal, you get what you get. Okay, the great blackout data. Okay, again, there's weekdays with a D, weekend days with an E for weekend, the number of bursts per day on weekdays and weekends. Okay, weekdays, again, you can see weekday, Monday, Tuesday, Wednesday, Thursday, Friday, 2 weekends, Saturday and Sunday. So day type may be related to the number of bursts per day on average. If I were to go ahead and fit y by x, we would say, does the number of bursts per day depend on the type of day? Click OK. We've got weekdays and weekends. And here, if I were to turn on my t-test procedure, we see that my confidence interval for the average number of bursts on weekends minus weekdays is -50 to -105. 0 is not inside that confidence interval. The t ratio, the t value is 6. The p value is below, it's about 0.0003, 3 in 10,000. We reject the null hypothesis of equality. 0 is not in that confidence interval. Equality would be rejected in this null hypothesis. Okay, so one more example. And this is an example that we had looked at earlier on, or talked. Did we talk about this? No, I don't think we did. So let's talk about this example right now, because it's sort of a cool one. At Ohio State University, an experiment was done to determine if people who hire others for jobs ever discriminate against those with handicaps. Okay. Now, there were 5 different videotapes that were a job interview. In each videotape was shown. And the person who is deciding the qualifications of the individual being interviewed for the job, they were all business majors with an emphasis in human resources. And so because of that, we could see, you would hope that they would be fair because they read the job description and they have a good idea about what is required of the job. And the job was one which did not require the ability to run or to walk or to literally answer phones. It was largely a job where whether you have crutches or hearing loss, it would not impact your chance of getting the job, or it should not impact your chance of getting the job. So they had these 2 job interviews, and of course, you'd think at first, maybe the people who have been interviewed one of them, maybe the crutch individual, is just outgoing and an A+ average person at Ohio State. Maybe the hearing loss person was like a C average person at Ohio State, and just was a bit of a bummer in the interview process. Actually, no. They're the same two actors with the same exact script. The interviewer asked the question the exact same way to the interviewee. The interviewee gave the exact same answers. The only difference was in the one interview, the person came in with crutches and set them against the wall in the background in the video, and in the other interview that we're discussing here, there was a clear, visible hearing aid in a notable color right stuffed in the guy's ear, okay? And so the only thing that should possibly impact the possible outcomes are either people are discriminating in favor of one group over the other, or maybe it was just bad luck. The hypothesis test is a way of saying, could it have been bad luck, or was it instead real? My null hypothesis and alternative hypotheses, they're pretty straightforward. My null hypothesis is the crutch group and the hearing loss group have the same mean average job qualification score. The alternative hypothesis is the crutch group and the hearing loss group are different on average. My test statistic T, again, you could see these are built into the slides that are online already. My test statistic T is 3.29. If I were using the shortcut for degrees of freedom, I would use 15 degrees of freedom, with my p-value being below 0.01. So verify that with 13 degrees of freedom, you could find your test statistic 3.29 in the t-table. Pause now and get your t-table out. Find your test statistic 3.29 and find then the p-value. Okay. Now that you've paused, I'm saying 13 degrees of freedom. That is the row that is beginning 13 degrees of freedom. I'm going to circle those here, 13 degrees of freedom. Where would 3.29 appear? 3.29 is somewhere in that range there, between 3.0 and 3.852. My upper tail area, thus, is less than 0.005. Less than 0.005. And the lower tail area is also less than 0.005. 0.005 on either end. The p-value less than 0.001. So the p-value is less than 0.001. What conclusion would you reach? Well, technically, you could say we reject the null hypothesis. And that is actually sort of technically correct, but often I will ask students to say in plain English what the outcome is. The conclusion is that these means are statistically significantly different. One group seems to be favored over the other on average. Or if you're writing a newspaper headline, discrimination exists in the hiring process. Not too hard, but still doable, okay? So let's talk about the 4 possible answers, 4 possible truths. Now, we don't actually know whether the null is true or not true, but one of them is correct. And if the null is true and we don't reject it, that's good. If the alternative hypothesis is true and we reject the null and believe the alternative, again, we're hitting the correct conclusion. If the null is true, but we don't reject it, okay, if the null is true and we do reject the null hypothesis, we're going to call that a type 1 error. If the alternative is true and we do not reject the null, that's called a type 2 error. And I have to apologize for my entire discipline here when calling these type 1 and type 2 errors. They're not really easily remembered. So I view it like this. In a court of law, innocent till proven guilty, you're going to believe not guilty until you're convinced of it. Could you ever vote to convict a person who's innocent? Does that ever happen? Yes. That's corresponding to a type 1 error. A person who is not, in fact, guilty, the null is really true, but we falsely conclude that a type 1 error, we falsely conclude that we reject the null. That's a type 1 error. A type 2 error is like acquitting someone who's actually guilty. Acquitting someone who's actually guilty. Type 2 error, the person actually is guilty of the crime, but we don't have enough evidence to convict. So a good place to hang your hat there. Now, I always ask students in class, which is worse, a type 1 error or a type 2 error? And they always say it depends, and I think I agree. But if I ask in a context of a court of law, which is worse, convicting an innocent person or acquitting a guilty person, and we always have some disagreements in the class until one student chimes in with, if you acquit a guilty person, the guilty person is not being punished for the crime. If you convict an innocent person, not only is the guilty person not being punished for the crime, an innocent person is. In the context of a jury context, type 1 errors are definitely worse. So that's why we say we should not do that. We should not vote unless we're convinced of guilt, because the asymmetry in the outcomes. Let's talk about a different study. Coffee and diabetes. The null hypothesis is that drinking 5 cups of coffee per day prevents the onset of type 2 diabetes. Okay. The alternative hypothesis is, I'm sorry, that's the alternative hypothesis. The null hypothesis is that coffee does not impact your chance of developing diabetes. The alternative is that coffee limits your ability to develop diabetes. It reduces that chance. What is worse? What is a type 1 error in this coffee and diabetes example? Coffee type 1. A type 1 error is, well, a type 1 error is, the null is true. So coffee does not impact your chance of diabetes, but we falsely believe that it does. So incorrectly or falsely believe that coffee reduces diabetes. Okay, so that's bad. I guess what's the social implication of that? People would believe that drinking coffee will cause them to limit their rate of developing diabetes. I guess someone might very well say, yeah, I'll just go drink more coffee. And we get a bunch of jittery people. Type 2 error. Type 2 error corresponds to, on the other hand, coffee consumption does reduce diabetes, but we can't spot it. Okay, so coffee helps, but we don't see it. Now, I would argue a type 2 error is certainly worse than a type 1 error. Because if people who develop diabetes can limit their risk of that by simply drinking coffee, that is something which we should really do. So, does coffee limit one's development of diabetes? I don't actually know, but I do know in the context of this one study what a type 1 and a type 2 error would mean. And if a type 1 error is no big deal, but a type 2 error is a serious problem, I would want to have a lower risk of a type 2 error. I'm willing to take a higher risk of a type 1 error. So how do we work that one out conceptually? I'm going to say I'm going to say the type 1 and type 2 error, it's all based in alpha. Alpha is the chance of a type 1 error that we're willing to take. If we're willing to take a 5% risk of type 1 error, we get then a corresponding type 2 error. If we want to lower a type 2 error, it's almost like the scale, the proverbial scales of justice, if you will. If one side goes down, the other side goes up. If you want to, in a court of law, lower your chance of falsely voting for guilt, you can tell, the judge can tell the jurors, don't vote guilty unless you're willing to bet your own life on the guilt. That's going to take some of the people who might have voted for guilt and cause them to vote non-guilty instead. So it's going to change the outcome. Or the judge could issue a different set of instructions, again, swaying the jury one way or the other. So my claim is this: if you want to literally limit your chance of a type 1 error, type 1 again is convicting a person who's really innocent, just don't convict anyone. A type 2 error, if you want to limit the chance of a type 2 error, a type 2 error corresponds to a person who really is guilty being convicted. If you want to limit that, convict everyone. Okay, so I'm going to claim this. We always go with an alpha of 0.05 unless the data context and the type 1 error and type 2 error practical implications mean we ought to choose a different level. If you want a type 2 error to be less likely to occur, then choose a higher value for alpha, like a 0.1 or 0.01. I don't care what alpha you use, other than, as long as you choose an alpha other than 0.05, you explain why you're choosing a different level for the test than 0.05. Again, 0.05 is the alpha you choose, the error rate of type 1 error you're willing to take. And if you think type 2 errors are horribly bad, maybe go with a 0.1 for alpha. If you think type 1 errors are horribly bad, go with a 0.01 for alpha. Okay, last thing right now, and that is association and causation. You all know that in an experiment, if there's a difference found between the two means, it's because of a causal relationship. The two groups are what cause the means to be different. In an observational study, you cannot conclude cause and effect, primarily because of things like confounding variables, common cause, or non-random selection. The other possibility is there's whether experiment or observational study could be just bad luck alone. It could be a type 1 error. If we see the difference between the two means, it could be spurious association. Okay, so that seems like a good place to stop. Enjoy the rest of your afternoon. We'll see you in the future.